We will now move on from mirrors and talk about spherical surface. So just to make it clear, mirrors are opaque objects. If we have light traveling, going to strike on the mirror, we know for sure that the reflected ray will be back towards the front side of the mirror instead of passing through to the back side of the mirror. Remember, mirror is opaque. But now when we talk about spherical surface, it's just that we have light entering from one medium to another medium, and they are separated by a boundary which is spherical in shape. You can think of light coming from air entering a spherical water balloon or a balloon filled with oil, or you can think of it as your eyes. So many situations you can try to imagine. So this is a spherical surface. When we talk about spherical surface, it's no longer the law of reflection anymore. Now we are going to move on to the concept of refraction. Refraction that we're going to talk now. Okay, so these are two different mediums. And when we say two different mediums, why do we call it two different mediums? It's because these two mediums here have different index of refraction. Okay, if the two materials have different index of refraction, we'll call that this is two different mediums. If they have the same index of refraction, you don't need to call them two different mediums anymore. Okay, so of course, since there are two different mediums, there's a boundary where you go from one medium to another medium. So for now, we know that based on this situation here, the index of refraction for medium A is smaller than the index of refraction for medium B. Okay, so now we place our object in medium A and try to see what kind of image should be formed due to refraction at this spherical surface over here. Okay, so the first thing is you assume this object is not glowing. Okay, for now we assume this object is not glowing, so there will be light striking on this object and get reflected off. Okay, so you have rays coming from any sources of light. These are not representing the color of the light, just representing different rays. So you have light coming from the sun, you have light coming from a lamp, you have light coming from the phone, you have light reflected off the wall. So light comes at different angles, and some of them get reflected in a direction that is not relevant for our discussion. It's just reflecting off to other angles. If you happen to place your eyes over here, then you will see that this object is over here. Okay, that's how light works. If you place your eyes here, then you see that the object is over here. Okay, but those are not relevant for our discussion. What's relevant is those light rays that are striking on the spherical surface. Those are the light rays that is relevant for our discussion. So when light ray strikes on this spherical surface, we know that refraction will occur. So how do we study the refraction that occurs at this spherical surface? It's very important for us to draw the normal line. Okay, when we talk about refraction, it's very important for us to know where is the normal line. Then only we can know if this is the incident ray, where will be the refracted ray. Okay, and since this is a spherical surface, we know that any line that goes from the center of curvature straight towards the spherical surface, that line itself will be 90 degrees to the spherical surface. So we call this line a normal line. Okay, so any line, if you want to find a normal at any point on the spherical surface, just extend the line from the surface to the center of curvature, and there you get your normal line. So now once you get your normal line, you can determine the refracted ray. So how we determine it is, we label the angle between the incident ray and the normal line to be the angle of incidence. Then we know that since the second medium here is having a greater index of refraction, we know that the refracted ray will be refracted towards the normal. The ray will be refracted towards the normal if the second medium is having a greater index of refraction. So you have to recall back Snell's law in order to know that it's refracted towards the normal. And to be much clearer, we have incident ray coming in this direction, and this is the angle between them. I call them theta A because it's a theta in medium A. Then the refracted ray will be smaller in terms of angle because we are refracted towards the normal. Okay, if you're coming from this direction instead, if your ray is coming from medium B towards medium A, the diagram will be similar as well, just that the arrow will be flipped. So now that your angle is initially small, but because you're entering a medium which is smaller in terms of index of refraction, you'll get refracted away from a normal. Okay, so if you work in the reverse direction, this ray is also true as well. It's refracted away from a normal. But now for our discussion, we're entering a medium with a higher index of refraction. So it's refracted towards the normal, smaller angle. So you know that this line, this refracted ray here will continue in a straight line inside the spherical surface. Okay, but if you want to determine the ray one by one by drawing normal lines, and find what's the angle of incidence, what's the angle of refraction, the whole process of drawing the ray diagram can be extremely time consuming. Yeah, so we don't want that. We want things to be simple, like the mirror case. We draw different rays that are easy to determine the direction of reflection. So in this case, I'm going to introduce a few lines that is easy to determine the direction of refraction and easy for us to construct our ray diagram. Okay, the first one will be the incident ray that is along the line that passed through the center of curvature. So in this case, the incident ray is in the direction of the normal line. So you can think of it as light striking normal to the surface. So if normal to the surface, the angle of incidence is 0. So you know that it will not get refracted away or towards normal because it is on the normal already. So you just pass through in a straight line, passing through to medium B and strike the center of curvature. There's no change, there's no bending because you are striking the surface at 90 degrees. So that's the first ray that is easy to draw. Second one will be a ray that is coming from the top point of the object and strikes on the vertex of this spherical surface. If you strike on the vertex, then this optic axis here will be our normal line already, because optic axis is extended from the center of curvature and it passes through this vertex, right? So it is itself a normal line already. So if it's a normal line, you can use that to guide if this is my angle of incidence, what should be my angle of refraction. Then you know how much bending by doing your Snell's law. You know how much you need to bend. Then you can extend the refracted ray and see where it coincides or intersect with the first ray that you draw. Okay, so for this case, we know that our image should be here, since this is our intersection between the two refracted rays. And just by seeing this, we can see that it's a real image because it's constructed by a solid refracted ray instead of extension of the refracted ray. It's solid ray that construct this image here, so it's real. Then we know that it's inverted because it's below the optic axis while the object is above the optic axis. And we know that it's diminished because it's smaller in size. Yeah, so the idea is still the same. That's what I'm trying to say. So we usually, when we draw a ray diagram, we replace the object with arrows. So I label this as an arrow. I label it O and I to represent object and image. Then now once the ray diagram is complete, I need to obtain 5 different parameters that are important. So the 5 parameters are the object height, the image height, the object distance, the image distance, also one more thing, the radius of curvature. So these are the 5 important parameters when it comes to refraction at the spherical surface. Again, ray diagram is nice to draw, but everything is a bit more qualitative when it comes to ray diagram. Let's say if you know the object distance, by drawing a ray diagram, you can only roughly get an idea it will be further away or it will be nearer. or it will be larger or smaller. You can get a qualitative idea. If you draw the diagram extremely accurately using all the geometrical tools you have, then yes, if you measure the length of the eye arrow here, you are able to deduce the height of the image. But a much easier way again will be using equations. So we'll move on from the idea of ray diagrams and move on to do things mathematically. Okay, so again, using geometry and trigonometry, geometrical optics, remember, we can derive a new formula, and this is the formula for spherical surfaces. Previously, it was 1 over u plus 1 over v equals to 1 over f. That's mirror equation. But now this equation is for spherical surfaces. And this equation here is replacing the role of the mirror equation. Last time the mirror equation is to express the relationship between the object, the image, and the mirror that is forming the image, right? Now this equation here is trying to relate between the object, the image, and the spherical surface that is refracting the object to form the image. Okay, so the way we use this equation is still quite similar. The N1 and N2, okay, if our light is experiencing a change of medium from 1 to 2, in that case our light is coming from here, medium 1, then enter medium 2, then we will write our equation to be N1 over U plus N2 over V equals to N2 minus N1 over R. So in this case, for this particular situation, N1 will be an A here, whereas N2 will be an B here, because our light experiences changes from medium A to medium B. So this is where we substitute the index of refraction for medium A. This is where we substitute the index of refraction for medium B. Okay, the N here, the index of refraction, is a value which is more than 1. So it can be 1.33, 1.2. It's impossible to be less than 1, and it's impossible to be negative. Okay, so for this thing, it's always positive, the value, index of refraction. Okay, the next thing we have U, V, R that we need to substitute in. For U, V, R, the concept of determining positive and negative, again, is extremely important. But the concept is still the same. For U, if the object is on the same side as the incident ray, then it's positive. Opposite side, then it's negative. So for this case, our object is in front of the surface. In front, I call this in front, I call this back. So if it's in front, the object is in front. The incident ray is also in front of the surface, same side. So our U here will be positive. Okay, so for V, the image, you see whether the image is on the same side as the refracted ray. This time it's refracted, no longer reflected. So if it's at the same side as the refracted rays, then it will be positive. Opposite side, negative. So image is at the back of the surface, and the refracted ray is also at the back of the surface. So both on the same side. So the V that we substitute here will be positive as well. Okay. Lastly, for R, it's similar idea to focal point. If you notice, for this situation, we have no focal point. Okay. So we usually just describe everything in terms of radius of curvature when it comes to spherical surface. Again, spherical surface, no focal point. You don't take half of it, then you call it this point the focal point. This is only true for mirror. So for radius of curvature, how do we determine positive or negative? Again, we see same side opposite. See whether the center of curvature is on the same side as the refracted ray or not. The refracted ray is behind the surface, and our center of curvature is also behind the surface. So both on the same side, so R here will be positive. Let's say our spherical surface here, it's like a convex, like a concave surface. So light strikes on a concave spherical surface, then enter another medium. A concave surface, then our radius of curvature, our center of curvature will be in front of the surface, whereas our refracted ray will be behind the surface. In that case, opposite side, then it will be negative. So a convex surface, then it should be a positive R. A concave surface, it should be a negative R. Again, don't try to remember convex what, concave what, because you get confused when you enter lens later. Just remember the C same side with the refracted rays or not. Same side, positive. Opposite side, negative. Okay, so this is the equation that relates everything together. So you know that the index of refraction is involved right now, and we don't have focal point for spherical surface. That's why the formula looks like this. Okay, I attach another formula here, the magnification here, just in case, because it's not written explicitly in your syllabus, but I think it can. I think it's still the same idea. Okay, the magnification is just the image height divided by the object height. The same idea as just now. Just that for your object and image distances, you need to include the index of refraction in the formula. How this formula is being derived is again based on geometry and trigonometry, but since it's not explicitly mentioned in the syllabus, I'll just write it here just in case you need the formula. Okay, so that's the idea for refraction at a spherical surface.